Hello everyone, in this video I'm going to explain principal component analysis. In many real-world situations, you may find a dataset with a large number of variables. This is especially true in consumer research. Datasets that contain many variables, or we call them as dimensions, are referred to as high-dimensional data. Sometimes the number of variables even exceeds the number of observations in the dataset. In some cases, you can just eliminate some of the redundant variables, but in many other cases, simply dropping the variables might result in losing valuable information. Principal component analysis, or PCA, is a useful dimension reduction technique that is especially effective when we want to reduce the number of variables but cannot completely eliminate any variables from the predictive model without losing important information. So PCA is considered as an unsupervised data mining technique, but we can also use PCA with supervised learning methods such as linear regression and logistic regression, where we have a large number of predicted variables that can be substituted with a smaller number of principal components. For example, let's say you are working as a bank administrator and you want to create a predictive model that predicts the loan approval. So loan approval response variable is equal to 1 if the loan is approved, and loan approval y is equal to 0 if the loan is not approved. And you have this list of predictor variables: income, education level, length of time at current residence, length of time at current employer, savings, debt, the number of credit cards. As a bank administrator, you want to analyze this data to determine the best way to group and report it. So you are going to here, to reduce the number of predictor variables from 8 to, let's say, 3, you are going to use principal component analysis. So therefore, it's going to be easier for you to analyze the data. So the next question is, how are we going to perform principal component analysis? Suppose we have n observations and k variables. Like in this case, we have 8 predictor variables. And let's say you have k variables x1 to xk. You are going to find a sequence of principal components PC1 to PCM, and the principal components are calculated as the weighted linear combination of this k original variables x1 to xk. The derivation of the weights involves a mathematical technique in linear algebra called eigendecomposition, which is outside of the scope of this course. We simply use analytic solver and R to derive the weights and the corresponding principal components. So here we have one example. In this example, you have the data for the nutritional content for 37 candy bars. The calories per serving, calories, total fat, fat in grams, protein in grams, carbohydrates, carb in grams. Here I'm going to show you how to construct principal components. So you can see the data here, and in this figure, the first principal component represented by the purple line. And this purple line is in the direction where the data vary the most. Or alternatively, you can interpret the first principal component as the line that is closest to the data. The blue line represents the second principal component. And the second principal component is orthogonal or uncorrelated to the first one. Here, x1 represents the fat and x2 represents the protein. In this example, with two original variables, fat and protein, or two-dimensional data, we can construct at most two principal components. As the large amount of variation in the data is now captured by PC1. And look at the variance distribution data here. First principal component explains 89.2% of the variation in the data. So, as the large amount of variation in the data is now captured by the first principal component PC1, substituting the original variables x1, which is fat, and x2, which is protein, with PC1 will result in little loss of information. So in your predictive model, instead of using fat and protein, you can just use PC1. And you can do this because PC1 explains almost 90% of the variation between x1 and x2. And PC1 is calculated as the weighted average of the original variables. Here weights are given in this table. So the weight for fat is 0.707107 times fat plus 0.707107 times protein. This is how we calculate PC1. But here when you look at the data, fat and protein, you realize that fat will dominate the protein because fat has more variability than the protein. For that reason, instead of using fat here and protein here, we standardize the data first and use fat z-score instead of the fat itself. So z-scores are calculated here. And now when you substitute the z-score, negative 0.7860, and protein z-score here, negative 0.8982, then you should get this result. And for PC2, now we are going to use the weights here. So the weights for fat now is going to be negative 0.70711 times fat z-score plus 0.707107 times protein z-score. This is how we calculate PC1 and PC2. In the following video, I'm going to show how to perform principal component analysis using analytic solver.